Welcome you to the next embedded software testing session, lecture 15 of Unit 2. We discussed about testing methods and test selection criteria in the previous sessions. We studied about equivalence partitioning, and in the last class we studied about boundary value analysis and equivalence partitioning both. And today we will discuss and study about state or event transition. Uh, we know the states how it's going to behave and the events, different events within the embedded system. Before that, I guess we will just do a test selection criteria for equivalence partitioning and boundary value analysis of the previous session. What are the things that we had studied? We know that the equivalence classes we are going to have in terms of valid and invalid, where the normal behavior of the system or normal expectation out of the requirements are under valid equivalence classes, and other side of the valid equivalence classes are nothing but invalid equivalence classes. And also we have studied about after we choose a good test case out of for these equivalence classes within that group, we will start the boundary for each of that equivalence class, valid or invalid, doesn't matter, just above that equivalence class and above the equivalence below the equivalence class in terms of the values. And basic idea is to reduce the number of test cases for a given set of requirements wherein the behavior is same. It could be valid or invalid. And also we studied an example boundary value analysis for n minus 99 to plus 99. We had seen minus 100, minus 99, minus 98 as one group, other is minus 10, minus 9, minus 1, 0, 1. Then we had 9, 10, 98, 99, 100. That means the boundary value we see just above the boundary and below the boundary, upper, lower, like this we are going to define it. So same thing is explained in the next slides in terms of minimum, just above minimum, nominal or average or normal it is called the middle one. Also it can be called as intermediate one, and we have a maximum and just above the maximum. So these are all will be covered in terms of equivalence classes. While doing the equivalence classes, we have to be careful identifying the tests, especially for the problems like next date problem, where we see we cannot afford to give April with a month of 31, which is not realistic, and we should have a knowledge of the requirement as well. Similarly, the triangle problem also we had a discussion where we are going to identify whether it's a triangle or non-triangle. Non-triangle inputs of no use, so we need to be defining what type of input based on the definition of the requirement, such as triangle or types of triangles. So that was what about the boundary value analysis and equivalence partition. We had an exercise. Probably we will touch base that exercise so that it will be more clear for you. So what we had exercise for boundary value analysis is that a temperature indicator, example a refrigerator, has two signals, so two indicators, red and green. The optimal temperature in the refrigerator is 3 and 8 degrees. That means between 3 and 8 it shows as green, whereas if it is below 3 and above 8 it will indicate as red. The temperature range can be divided into 3 intervals. We know that from infinity to infinity means here any number on the lower side till 3 degrees, but not including 3 degrees. It is less, just less than. Till then we are going to include and from 3 including 3 till 8 including 8. Similarly, not from 8 but just above 8, 8.1 or whatever it is till the another infinity value such as 100, 200, 300, whatever the capability of that particular temperature sensor. So for this example, when using a boundary value analysis, there should be one test case for each boundary in every equivalence class. So there are about 5 test cases identified for equivalence class for this example. The first one being test case 1A, negative infinity, even minus 273 is a little hard to create and furthermore not very likely to occur. That means the temperature need not be minus 273, the chances are very less. So we could give something like 50, 70 max. So next one is test case 1B. Here we have the problem of being close enough to the boundary, since being on the boundary is outside this interval. Is 5 valid digits a good estimate? So basic thing is can we have a 3 digit or 4 digit or 5 digit? It's up to the specification. We should have an answer in the specification how much it can go, or if we don't have, we should have a knowledge of such sensor systems where the sensor is capable of so and so ranges. Though the requirement says I will take care of only 3 and 8, we should have a knowledge of the underneath sensor or the hardware which is capable of taking a max both the sides. So that is why test case 1A 1B could be go either way. Then we have test cases 2A and 2B, the second set of test cases. Both boundaries are inside the interval, so these values are the ones to choose. That means there is an interval above 8 you can see. So one of that. Similarly, we have the other one also above 3. Sorry, below 3K. It could be anything till minus 10, 20, depending on the capability of that sensor. Then we have test case 3A, same discussions as 1B on the other side, and test case 3B same as 1A on the other side, that is on the plus side. So that is how we can have a boundary value analysis for this example. Okay, now the last test selection criteria or technique that we will discuss today is about state or event transition. So what is a state? Let us briefly understand about a state. Many embedded systems or parts of embedded systems are basically being developed with the help of state-based behavior. This is something at different modes, which we can also call it as, where the embedded system will move from one to other one. That means it has a predefined set of actions or executions for such mode or such event. So based on the criteria that it enters, or based on the criteria that it exits from that particular state, it has a number of behavior that it has to behave. So basically, many of the embedded systems are partly the pieces of the embedded systems can be implemented with the help of state-based behavior. So state-based embedded systems or state machines is also called as, is being implemented in many of the embedded systems that we can see, especially the complex systems in the industries such as telecom or a mobile, any GPS or GSM system. You take the automotive, for example, we have engine control systems where engine control has many features or functionalities driven based on the different states. Similarly, we have aerospace products or avionics subsystems having state-based or state-driven applications. In designing these systems, state-based modeling is used. So basically, state machines or state-based embedded systems, so they develop with the help of modeling, because modeling is an important concept in developing such states. So we have state diagrams and all that. Maybe we can have a small session on what is a state-based modeling for the development purpose. Similarly, we can understand the state or the model-based testing. I think we are going to study that model-based testing in one of the class in the future sessions. So models composed during this process serve as a basis for the test design. That means all these models are the basis of designing the systems having state-based behavior. So the testing is called model-based testing. The purpose of that state-based test design technique is to verify the relationships between events, actions, activities, states, and state transitions. Transition is something like the entry and exit of different states from one state to other state. The movement is called transition, or the entry exit from one state to entry to another state is called a transition. So upon occurrence of certain conditions, those conditions are called events. Based on those conditions or the events, the transition will occur. The events could be some actions. As a result of event, some actions need to be taken care. As a result of action, some activities are going to be happening or executed. So that is how a state transition will happen. By using this technique, one can control if a system state based behavior meets the specifications set for this system. What it means is, with the help of this technique, we know that how the system is entering and exiting from state based behavior, and testing this, we know that how we are going to meet the specification set for this system. Testing different conditions or different events of state transitions will help us know whether it is transiting or not, whether it is doing an entry to the next state, and whether it is exiting from the previous state, etc. All this can be known with this technique called state transition testing. And state based behaviors usually are represented using tables or activity charts or state charts. So just to name them, I will put those so that we need to be aware of this as an embedded software tester. So basically, state based systems are represented with the help of tables, state charts. We will study little on this, how they are. Tables also will be there. Like there are a few elements which are part of these tables. The table is also called as lookup table. Using function pointer in C, I would say this is basically implemented. It's a very critical aspect in embedded systems where we have a complex mechanism in terms of different states and numerous events triggered based on numerous signals are occurring. That means we have I will try to suppose one state, this is another state, let us say, and we have a state change between these two, and of course we need to define a state entry also. how the state can be entered, and how this state can be exited. So let us say this is a state 1, this is a state 2. Two states are there. These two, like this we can have multiple states in a embedded system. Suppose state 1 needs to be entered, so there are certain events that needs to be E1, let's say, or E2, E3. Systems under satisfaction of one of the events or all the events could result in entering into the state 1. Suppose let's define the state 1 as initialization. So upon power up, there are certain conditions. Power up is one condition. The system will enter into init state. Once the init state is complete, that means there are different activities. The action is two activities such as initialization of hardware, software, etc. So this state will be complete. So once the state is complete, that means the conditions that are to be, or the actions that are to be concluded or completed within the state are done. So that means we are good for going for next state. That means the exit criteria is satisfied. That means we have an entry criteria in state 2 is satisfied. Here it is entry, here it is exit. So we know that state 2 is entered. This could be a main application. Similarly, we can have next state like this with the help of the state diagrams, and this state can go to first state also based on the reset or some events that will result in switching between the states. So that is what the definition of state. This state diagram, this is basically state diagram. These state diagrams are basically represented with the help of text. I think I will explain with an example of how tables will look like. The table will basically define the states and events. State charts also will define complete the state machine, entry, exit, all the values and everything. And we have a lookup table identifying the functions which are responsible for entering into different states. These are implementation aspects that are part of the embedded software systems. So it's very important to know the state transition mechanism in order to test it. So how we are going to test it? Mostly with the help of model based testing, because state machines or the state transition systems are basically based on modeling. We will study about the model based testing in the next class or next sessions. So that is about state transition. You can see an example of states. This is again from the book Embedded Software Testing by Bart Brockman and Nordenboom. So here he has depicted a state machine, a state chart basically, that is of a tape recorder. Let's try to understand from the sake of understanding the states and the state chart. Okay, so there are three states. You can see the grade 1 off, on, recording. Simple. So tape recorder can be in off state, tape recorder can be on state, tape recorder can enter into recording state. Right? Okay. How the off state will enter? So there is a small dark arrow you can see, that is from the switch off to switch on, probably you can say. So we have a switching mechanism. which will help in terms of going to the first state. So that is why it is called a test state. And tape recorder can go into on state with the help of some operation or some action. There is nothing but an event. Event power on initialize system. That means once you power on with this power on switch and you connect to the power supply and make switch from off to on, it will enter, right. So the event is event power on. So action is initialize system. So three things are important: state, event, and action. With this state is defined, or switching to the next state is defined. Next is on. What is going to happen within on, or what are the events or actions that are going to be taking place within this state? That is nothing but on state. You can see a circular arrow. Transitioning to self. This is an important term. When on, it can be there in on only, because user has not done any operation. He has just powered on, so it is waiting for the user to operate further. Either could be play, or as you can see the next state recording, or anything. So till then it is going to be this event. So that event could be called as event reset or initialize system. Again, that means in on, it is just waiting for the reset event to happen, or it is waiting for the initialization, any further initialization for the next step to occur. The next to that is recording. So upon a user presses the recording button, what will happen is it will enter into recording state. The event is called start recording, and the action is start record. So there is a guard. The term is called guard. So what it does is from on to recording, the guard will be triggered. So it is called guarded transition. And of course, from recording we can again go back to on state by stopping it, right. So we can have another event called stop recording, and the guard could be the next one. Similarly, from recording to off we can go, but there are tape recorders we see we should first do a stop, then go for off. So likewise the different states are entered and exited. So three terms are very important to understand: state, event, action. So that is about an example of states, how the state transition is going to happen. Here we can see three. This is about the state chart. So what we have seen, there are different events, right. So those events are explained in the next table, next figure. Okay, so let's do a small understanding of this. So there are two levels of explaining this events, or the flow between A and B. You can see the upper side is A, lower side is B. A simpler term we will try to understand. So what is told in the book is that synchronization between orthogonal inputs with storage of event information. That means two orthogonal events are going to occur with different states, and how they will be taken care is what is being explained. So there is a state 1A, state 2A, state 3A in the first orthogonal section, and it will enter into the next orthogon with the help of state 2B, state 3B, state 1B. And for switching between these states, there are different events that needs to occur. So state 1 A is been entered with the help of power on, then event 1 will go to state 2A, and from state 2A event 2 can happen, it will come back to state 1A. And similarly state 1A to state 3A directly we can go, the event is 3. Similarly from 3A we can fall back to state 2A with the help of event 4. Then also there is a second orthogonal region, the event 3 can also trigger to the next one, which will result in state 2B, state 3B, state 1B, etc. State 1B can be directly entered with the help of this. So there is a synchronization mechanism that is detected here with the help of that one round button. So let us not go in detail about this, but what we have to understand from this is that different states are responsible for taking into the inputs from different events and moving to the next state. It is called switching. And three terms are state, event, action. These three we need to remember for embedded software testing. Okay. Now the behavior of the system can be classified as three types. The state transitioning behavior is divided into three types. Simple behavior, the system always responds in the exact same way to a certain input, independent of system history. That means it won't care what has happened in the past, but it will behave the same way all the time for certain input. The second type of behavior is continuous behavior. The current state of the system depends on its history in such a way that it is not possible to identify a separate state. That means based on the history it will decide whether it will switch or it will not switch. So basically it's not possible to identify a separate state. It's a continuous behavior. The third one is state based behavior, where the current state of the system is dependent on the system's history and can clearly be distinguished from other system states. That means we know where the system is lying in this sort of a behavior. That means the current state of the system is very much dependent on the system's history, but it is possible to identify a distinguished state from the other state where it is. So this is a state based behavior. Here second one is a continuous behavior, where we don't know or we are not able to identify the states, specific states for that particular input. It is again depending on the history. Simpler behavior, we have a clear input and it is very much independent. So it will behave all the same, all the time, same thing. That is what it means. Okay. So now let's move on to the next thing, functional behavior in the state machine. So basically we need to understand what are the functionalities it is going to execute. So what we understood from this is that there are different actions based on different events. So all these are all part of the functions, one or the other way that that particular piece of software is going to behave. Those functions are something like procedures or different subsystems which are driving the embedded system to switch between the different states. So all this functional behavior we need to test it and cover all the states that the software enter and exit. That means the coverage is very important for a particular state as per the specification. So we need to create test cases as per these three steps: reaching each state, how to reach a state, using every transition that from the default to switching. That means every transition we are going to cover with a base to the next state with a different transitions. Similarly, the next one is for each possible chain of transition. It means end to switch coverage. That means maximum of possible transitions in the complete path of that we are going to have it. So we are going to create test cases accordingly. So state machine based testing it is called is a quite useful model based black box testing technique. Since any type of functionality that can be represented as a finite state machine can be tested using this technique. So finite state machine and all are beyond this class, but you can study that in embedded system basics where we have different state machines defined and its behaviors are detailed. So state machine based testing will help in identifying the issues with those implementation of state transition. So some more details. The first step what we do when using the state machine testing is construct the model itself. That means we are going to construct the model, how the model is going to be behaving. So we are going to, with the help of our test, we are going to trigger some of the inputs so that the model is constructed. Sometimes state machines are used by designers and constructors as implementation tool. As I said, the models are used or developed. So in those cases, the state machines can, of course, be used directly. We can directly use the state machines. Otherwise, the state machine model has to be constructed based on the requirements by testers. That means, as I said, model based testing where we develop the model first, then we define the states, or based on the requirements, it depends on the simplicity or the complexity of the requirement or the underneath system. We are going to develop the state machines. So what will happen is during the construction of this state machine, faults can be there. So the key properties with a state machine is that all input types can occur regardless of the state of the machine. Implemented through model based design, or it could be implemented directly from the requirements. The requirements should be so good and clean that it is implemented directly from the requirements. So same way we can test it. If the models are available, we are going to attack the models to test it. If the requirements are there to implement, we need to understand the functionalities that is underneath the requirements. We now test the different states that are responsible for the state machines. Okay, so there are other details like the model based testing and all. Probably we will study that in detail in one of the model based testing class. So basically, we need to the strategy is to elaborate or focus on the transitions. So very important thing. You need to understand the concept of transitioning, as I said in the earlier slide. Transitioning which will happen with the help of event, and event will result in action. So all these are part of the state n. I would say n. So it's very important from different states, from 0 to state n, and from state n to state m, a, b, whatever it is, all are based on the transitioning. So we need to have a strategy test on the transitioning between the states. So 0 to switch coverage requires one test case because we know that the one transition, and for each possible transition we have a one to switch for one possible transition is there. So likewise we have for n to 1 consecutive transitions where we have a n to switch coverage requirement is there. So that is how state transitioning testing is taken care, where transitioning has to be understood very well. Okay, now having understood the different behaviors and the states, events, actions, we need to categorize the faults. So what are the fault categories that are there for incorrect state behavior? We know that states can mislead to different errors or faults, and how we can categorize those faults in the state based embedded system behavior. The first is that the state chart do or does not represent a correct translation of the system's functional specification. That means it is not actually presenting the functional transition. The state based test design technique is not capable of revealing these types of faults because the state charts themselves are used as the basis of the tests. So we will not be able to identify the faults simply because our tests are based on this state based uh, functional specification. If there is a problem with that specification itself, the switching and all that, we will not be able to find uh, the problem. The second cause is that the state charts are syntactically incorrect or inconsistent. That means these faults can be revealed by static testing. So these are some of the issues that we can come across while doing the embedded software testing using state transition. So this type of faults we could reveal while doing the testing itself, or uh, the strategy needs to be reworked, or alternates we need to find out after finding these faults. So second will happen because syntax errors are there, or syntactically it's not implemented, or it is not consistently behaving. The implementation is wrong. So these faults can be revealed by static testing. So static testing anyway we will study in detail. So we have analysis or inspection methods. With the help of that, there are additional aiding tools such as checklists or any other tools. With the help of that, we can reveal these kind of syntactical or inconsistent issues, like instead of input, output is mentioned in the events. Those kind of problems are found out with the help of that static testing. If the faults found this way are corrected, then the state chart constitutes the basis for dynamic testing using the state based test design technique. So after the static testing, this will be used for doing the state based testing. The third cause is the the translation from state charts to code. That means how the code is implemented from the state chart, whether it is implemented exactly what is required for transitioning. That is where the fault category lies. It is becoming increasingly common that this translation is performed automatically. That means we have a generator, code generator from the models such as artisan and all that model based design they do. They have a auto code feature wherein they generate the code from the model itself. With the help of that, they integrate and execute the code. But it is not 100%. The code that is developed from the model using the auto code, still we need to fine tune it to make it exactly what is intended. The code generated this way an exact representation of state charts behavior. The use of the state charts as the basis for this design in this case is therefore not useful, and the application of the state based design technique is superfluous. However, if coding based on state charts is applied without the use of a generator, then the state based test design technique should be used. It means autocode generator we are not using it, then we should be stick to testing with the state based test design technique what we have seen with the help of transitioning and state based testing technique. The next we will study in detail about the faults. Different faults can occur for doing the state charts and the software having implemented the state techniques, state transition technique. States can have issues. States without incoming transitions, that means without any inputs, specification and or implementation fault. That means states are happening without any transition. Second type of faults can occur, missing initial states. That means the entry itself is not there. All paths in a state chart must be defined. In the case of a transition to a superstate in which the resulting substate is not indicated, the superstate must contain an initial state. That means where we have we don't have a resulting substate, there should be a initial state at least to switch on. If the initial state is not indicated, the state in which the transition terminates cannot be predicted. We don't know where it's going to be terminated. The states specification or implementation fault. Specification could be wrong or the implementation could be wrong. So this is one of the faults, missing initial state. Third one is an additional state. That means an extra state, something like the system turns out to have more states than it is represented in the statement, which is something like a dead state or a redundant state. So it is again a problem with the implementation. The implementer has added more states unnecessarily, so that those paths cannot be covered, or that is a fault. The fourth one is a missing state. That means one state is missing. If it is supposed to have 4 states, but instead of that 3 states are represented with the help of the code, then that is a fault. The state that is shown on the state chart, but it is not present in the system. The other one is states are there, but one particular state is corrupted. A transition takes place to a non-valid state, or the state itself is not existing, but the code is that it is going to go somewhere, but it may crash or it may do a unpredictable behavior, very difficult to test sometimes. So it's an implementation issue basically. So we have 2 specification or implementation issue where we don't have a incoming state or some of the initial states are missed, and implementation wise we have redundant states or addition states. We have missing states where there is no state at all, and the states are there but it is corrupted, so that system will not behave properly or it may crash. So this is some of the faults that can occur for the state charts. The second category is on gods. So gods it should point to a transition and not to a state. So gods are something like what I said in the earlier thing. It is a event where continuously that is happening in terms of one example you can say my tape is switching to is in, that means it's present. So it's a guarded transition. So what are the faults that we can have in the guarded or the gods? So God must point to a transition and not to a state. Always God should be identifying the transition. So what transitions are used as a transitions? So transitions must have an accepting and resultant state. Conflicting transitions should not be there. An event triggers a change from one substate to another substate, and at the same time it triggers a transition out of the superstate. That means the main state itself is not able to achieve. There is a conflict between different transitions. It may happen to that state or this state while happening that it may be out of the main state itself. So this results in the fact that a certain substate is no longer within reach. That means it will never go to that substate, because in a complex systems we have seen many main states and many substates. So without coming to the main states, it is not possible to go for a substates. So I will try to draw as simplistic way possible here. So there is a main state, two main states are there, and there are small substates pertaining to this main state, suppose, and we have a transition between these, we know, transition between these two we know, and transitions from this we know, this we know, etc. This is the major main state. This is called super state, and these are substates, and we should have a mechanism to switch to this substate through this main state. Similarly, the other way also true. So it cannot be conflicting for state transition between the substates to main states and the main states to substate. It should always be predictable, such a way that the state transition is smoother. That's what the meaning of the reachable substates should be reachable. That's what the meaning means. So confliction should not be there for state transitions. Okay. Next one is missing or incorrect transitions. That means, as I told in the previous states itself, the states are not there, but transition is happening. Sorry, there is, the states are there, but the transitions are not proper, or it is missing. The resulting state is a neither a correct or nor correct in terms of switching there, transitioning. So other one is the missing or incorrect actions. So we know that different actions are there due to which the transition will occur. So there has to be action that could be missing, or the actions are improper. So incorrect actions are performed as a result of executing a transition, specification issue, or implementation issue. So all this could be because of specification also, or it's an implementation problem also. So transitioning and states, these two are very much important in terms of testing the embedded systems where states are implemented. So fourth one, the last one is, and of course we have a miscellaneous, we will quickly go through that also, events. So we know that events due to which the states will transit. We have a missing event, the faults could be there in missing event, an event is ignored. It means the events are not happening. Specification and or implementation fault, then there is a hidden path. That means events are happening, but we don't know the reason why that event is happening. A reaction to a defined event takes place, although this reaction is not defined in the state chart. That means snake path, it is also called as a snake path. The implementation path fault purely. So some events are happening, but there is no reason for that. So not due to some actions or something like that. That events are happening. That is nothing but a hidden path event. The third one is the reaction takes place to an undefined event. That means a reaction is happening, but there is no event. It's also known as a trap door. That means it's a implementation fault. So reaction is there due to something, but there is no event as such. This is the fourth type of faults that can be there in the state-driven embedded system. The last one is miscellaneous. This typically talk about synchronization in an orthogonal region. A synchronization substate is situated in one orthogonal region without a connection to an event in another orthogonal region. That means we have two spheres, having different state switching, but there is no proper synchronization between the two regions. A wrong implementation of the synchronization pseudo state can lead to rarely or not at all reachable states, no synchronization at all, or to a barely detectable deviation from the required system behavior. So this is basically talking about the synchronization between say subsystems, where both the subsystems, let's take two subsystems, so both subsystems have implemented the state machines. So in this case, so the events that are happening within these subsystems and switching between these subsystems or interaction between these two subsystems are purely based on the synchronization. So the synchronization has to be intact in order to work it properly. So this is what is the fault could occur in the miscellaneous region of the synchronization, and we will try to have a small table state transition fault categories coverage, how this is defined. This is the last slide. So coverage of the fault categories, we will define the different faults, so 1.1, 1.2, 1.3. So there is a checklist, state transition technique we can apply or not. So based on this, these fault categories are applied. These different fault categories are all what we have discussed here: 4.1.2, 4.3, then 3.1, 3.4, 2.1 gods. States have 1 to 5. Likewise, we have different faults. So we have a checklist. Checklist in a sense whether it is a ticked or it is wrong, something like that. We are going to have it while defining the state transition technique. It's very important so that the coverage is very clear. So that is what the meaning of this. We can have this, this, this as not covered in our embedded software testing. So we know that this checklist, with the help of this, we have the state transition technique is happening now. So this fault category can be tested by both a checklist and the test design technique. It means we are going to have a coverage for all. The 2.4 can be covered with the help of test design technique and with the help of checklist also. Category 4.3 is not covered by the test design technique. Error guessing is in this case one available option. Error guessing the technique will probably touch base. So error guessing is something like we identify an error or a fault by guessing what could be the problem. So this will happen during the dynamic execution only, because the tester will have an understanding of the system, how it is executing. Only when he is doing some other tests, he will guess some errors while doing some other tests. So 4.3 is what type of thing is reaction takes place to an undefined event. So we know that as per the specification we would have tested, but what will happen during the test is that some reaction is happening, but there is no event defined for that. So trap power it is also called. So that is what the category is about. So this can be done with the help of error guessing or thorough analysis or inspection of that. So this will help in terms of coverage of state transition. This is an elaboration of this. So we will continue the state transition with some exercise and other testing mechanisms and methods in the next class. So that is the conclusion.